So I really didn't expect so much people, so I'm not sure if there's like a sudden interest on philosophy or people just doesn't know closure. Uh, I don't know. So, okay. Let's start with my bio, right? Everyone starts with this. So Juan was just a regular kid until one day he bet his soul with the devil and lost. Then he suddenly learned to play blues and started working with technology, making fortunes in the dot-com bubble. He studied physics, where he couldn't find any evidence for, and philosophy, where he couldn't find any good argument for the existence of souls. Given an approaching deadline set by the Dark Lord, he decided to move to Israel and learn Hebrew in order to read God's words and seek atonement for his sins. Nowadays, he works with front-end technologies since he couldn't find anything more self-flagellating to do. So, as the Coen brothers would say, this is a true story. Okay, so what is programming? Let's start with a tale, right? It's good to start with a story. So, five philosophers sit at a table with bowls of spaghetti. Forks are placed between each pair of adjacent philosophers. Each philosopher must alternately think and eat. I think you know this problem, right? So the first philosopher thinks for a little bit and says, programming is like the human body. There are parts that conduct actions like hands and legs, but these are commanded by a central control, the mind. The mind is not only capable of commanding the body to perform tasks, but to produce ideas and to think about these ideas in the most abstract ways and understand the world around it. We can know about ourselves both by reflection and direct contact with our ideas, feelings, and sensations, but also investigating ourselves as objects in the world. The second philosopher thinks for a little bit and says, no, programming is like an ideal city. The architecture is formally planned to perfection. Everyone does everything to the best interest to the community, and no vices are allowed. The city will create an unbeatable army by selecting only the strongest and bravest and train them through the most rigid discipline. The city must be ruled by kings, educated in mathematics and logic. The third philosopher says, programming is not like that, it's like a real city. So some cities start by chance, some cities are planned, but it evolves based on real human needs. Individual parts are planned, built, and evolve according to these needs. The city must be ruled by pragmatical leaders who put the population interest first. The fourth one says, no. Programming is a postmodern activity. All your suggestions are grand schemes and are simply lies to children. Programs are actually systems, constellations of parts built in completely different ways, connected arbitrarily. While you are discussing your grand schemes, people continue building big balls of mud. Let's instead study this mud and improve from there. And then the fifth philosopher says, hey guys, can you pass the fork? I'm really starving here. But no one replies, and he insists for hours, days, until he finally dies. So what is our agenda? See, my keynote also died. So. Cool. So we're going to go over five small parts. First of all, I'm going to talk a little bit about how I think philosophy can deal with these problems. We're going to take a look at the history of the paradigm wars, and then we're going over each of the paradigms. This is supposed to be more like a one-on-one. If you were to have like a philosophy and computer science in the university, this would be more or less the content, I think. So what the hell is this connection between programming and philosophy? So there are many ways in which philosophy and computer science already intersect, right? Especially in the philosophy of mind, artificial intelligence world, but also tangentially, like in computer ethics, right? This is not precisely computer science, but it's sort of related to the domain. But in this presentation, I will focus on another way, and I'll show this way using a citation from Timothy Colburn. So he says, computer science is ripe for the good old-fashioned analysis that philosophy can provide for any science. Thus, a perfectly reasonable role for philosophy is to attempt to place computer science within the broad spectrum of inquiry that constitutes science. The concern here is to deal with the inevitable identity crisis that crop up in the self-image of any adolescent, which computer science certainly is. Philosophy should address questions like, what is the relationship between mathematics and computer science, is there a sense in which computer science is an experimental science, and what are the ontological implications of computer science? So, paradigm wars. So it appears that there's really no consensus on what programming is about, right? It seems reasonable to be so. After all, this is an activity that exists for a relatively short period of time, 50, 60 years. In this time, it changed the way we perform almost all of our other activities, and it carries no smaller promises than, virtual worlds, artificial intelligence. On the other hand, the disagreements are huge and apparently irreconcilable. So the way to put it, there's this quote from an article called Three Paradigms of Computer Science, where they say that computer science textbooks, classics, articles, conferences, curricula are dominated by radically different methods of conducting research and teaching. So mathematical methods of investigation guide the research of computability, automata theory, computational complexity, and the semantics of programming languages. Design rules of thumb, extensive testing suites, and regimented development methods dominate the branches of software engineering. And the methods of natural science, which combine mathematical theories with scientific experiments, govern the research of artificial intelligence, machine learning, so on and so on. And then he goes on saying like that in certain universities, the Department of Computer Science belongs to a different place, mathematics, science, I don't know. So I just made like a quick table so you can see what he's saying. He's saying like, we have these three paradigms they call scientific, rationalist, and technocratic. There's a certain ontology around these things. This means what a program is, right? How do they define program? The sort of knowledge that you can get based on these objects, and the methods, and of course the department that these approaches are in the universities. But how can it be that programming is seen in so many different ways? The thing is that established areas of knowledge had what we call today a pre-scientific period. And this is defined by a period where their object and method were either not mature enough to produce major breakthroughs, or were disputed to the point of not having a general consensus around their practitioners. But the thing is that even mature areas of knowledge, seen from an historical point of view, seem to contain a dynamic process of breakthroughs leading to redefining or at least refining the understanding of the object and therefore the activity itself. One example is like the battle that is going on in the physics department between particle and string theories, right? Some claim, especially given the lack of experimental results, that string theory is not physics. They think it's just a mathematical thing dealing with something else, not physical objects. While others say that, well, we're using mathematics, but our goal, our object is still physical objects. We can also look at the introduction of probabilities of aggregates by the kinetic theory in the 18th century. So it was introducing probabilities in a domain that people expected to be purely void of this sort of thing, completely deterministic. And I would say more decisively, we can see that even the empirical method was not central to what was called physics before that. When Galileo pointed his telescope to the moon and he invited the scholastics to look at it and see his research, they didn't want it, and they came with a priori arguments that his theory was not even possible, logically possible. So he sent this letter to Kepler, where he says something like that: "My dear Kepler, I wish that we might laugh at the remarkable stupidity of the common herd. What do you have to say about the principal philosophers of this academy who are filled with the stubbornness of an asp, and who do not want to look at either the planets, the moon, or the telescope, even though I have freely and deliberately offered them the opportunity 1,000 times? Truly, just as the asp stops its ears, so do these philosophers shut their eyes in light of truth." But nowadays, we don't even equate these early efforts with physics. We call them Aristotelian physics, scholastic physics, anything to distance these efforts with what we call physics nowadays. But what links this pre-scientific physics with the current one is that it was probably, interest in the same objects. No one, I guess, would deny that Aristotle was talking about motion, right? The only thing is that the methods that were employed in the past, which like in the medieval period was mainly commenting Aristotle and Plato, were not fruitful, and then it required like rethinking these methods. But what seemed peculiar to the problem of the nature of programming is that there's wide disagreement not only in the object, not only in the method, but also in the object itself. The disagreement that seems to be the most fundamental is the one regarding the object, since all these presented characterizations, they follow the method from the object following, the current structures of the sciences. It would indeed be very creative if computer science would come up with like a completely novel method and a novel explanation of this object, but in this presentation I'll try to focus on these three variations. So the first one is programming as science. So in the 50s, I would say that the majority position about programming was the scientific one. That's certainly related to the fact that the very invention of computers was sort of related to this grand narrative of creating a thinking automaton, a robot, right? In hindsight, this seems really strange because by now we know that is a very hard goal to achieve. It seems that we put the cart before the horse. But it's still remarkable the confidence in which researchers by that time would make analogies and draw quick conclusions relating programming to human thought. Look at this example. So this is John McCarthy saying, well, to represent algorithms by symbolic expressions in such a way that significant changes in the behavior represented by the algorithms are presented by the simple changes in the symbolic expressions. Programs that are supposed to learn from experience change their behavior by changing the content of the registers that represents the modifiable aspect of the behavior. And the coolest part is this. For a certain point of view, having a convenient representation of one's behavior available for modification is what is meant by consciousness. That's a little bit controversial. So if programming is to be properly scientific, it seems that it must have as an object something that is a natural entity. The relation of program and mental processes is not meant simply as a constructive analogy in this understanding. It is sort of an identity. The nature of this identity is hard to fathom, but must be based on the possibility of translating patterns encoded as programs in a machine and patterns of neural states in our brains. So if software is a pattern first and material embodiment of pattern second, then it can be ported from one substratum to another. It is liftable. That's the main concept here. The pattern embodied in magnetic fields on a disk can be lifted from the disk and transposed to solids and blanks on the cells of punch cards and vice versa. It is this property of software that gives workers in the field of artificial intelligence their hope of success. If the mind is reducible to the brain and the brain is a complicated pattern of neural switches, then the mind can be lifted and reinstalled in a silicon substratum, and maybe otherwise as well, right? But this assumes that, well, the mind is reducible to the brain. Probably that's the less controversial assumption. Brain patterns are deterministic and understandable. That's probably a little bit more controversial, but the hardest one is that this position may also require the assumption that there is or there will be a solution to the hard problem of consciousness. Simply put, this problem is that it appears that a simple functional explanation of how the brain works doesn't seem to account to explain our subjective experiences. So this is the hardest problem in this field from the 50s until today. But moving from the mind process idea, there are also some views on programming as science that doesn't really rely on this ontology of mental processes. So let's see one example. So here, this is from, I think it's a Turing lecture. Each program is an experiment, and its behavior offers clues to an answer. Neither machines nor programs are black boxes. They are artifacts that have been designed, both hardware and software, and we can open them up and look inside. We can relate their structure to their behavior and draw many lessons from a single experiment. Inspection of the problem in the light of a few runs reveals flaws and let us proceed to the next attempt. So in this account, programming is scientific simply because we apply an experimental method, right? But the difficulty of this specific formulation is multifold. If a program is an experiment and its behavior offers clues to an answer, we can rightfully ask an answer to what, right? For if a program is an artifact, there is a clear disanalogy with all the other natural sciences. For these are sciences occupied with nature, and if they test artifacts, it is only to ascertain their correctness as a mean to ensure the experiments yield reliable information about their ultimate objects. And even more importantly, it seems that any knowledge that we derive from testing a program is about the program itself, and following Quine, everything behind the program. So the machine, laws of physics, logic, everything. And not general hypotheses. So Tony Hoare says, Computers of the present day are very complicated and rather poorly defined. As a result, it is usually impractical to reason logically about their behavior. Sometimes the only way of finding out what they will do is by experiment. Such experiments are certainly not mathematics. Unfortunately, they are not even science, because it is impossible to generalize from the results or to publish them for the benefit of other scientists. But this sort of empirical research can yield some generalities. But I think these generalities are more akin to rules of thumb, guidelines, and this seems more in line with the idea of programming as engineering. With time, this naive enthusiasm of the scientific view started to fade, and here's Fred Brooks' assessment of this thing. So he says that, this is in 90-something, so he says, it is time to recognize that the original goals of artificial intelligence were not merely extremely difficult. They were goals that, although glamorous and motivating, sent the discipline off in the wrong direction. So he says that in this paper, he argues that we could have done much more if we had focused on practical things from the outset, instead of trying to make minds right away. In any event, this view haven't yet died, or at least its main goal still motivates, and will always motivate, even if our aspirations are lower. But its survival as a full-blown paradigm depends on major breakthroughs in our understanding of the concept of mind. So programming as mathematics. Many computer scientists have expressed the opinion that computer science is simply a branch of mathematics. Let us first establish this position. So computer science is an exact science, and that all the properties of a program and all the consequences of executing it can, in principle, be found out from the text of the program itself of means of purely deduction reasoning. So how to use purely deduction reasoning doesn't really need to be defined on this presentation. Suffice to say that this position depends on the idea that in some sense a program can be seen as an ideal entity. That is, as a general characterization, something that doesn't have a spatial location, doesn't have causal powers, and so on. In any event, the most convincing way of doing this is in the realms of logic, and mathematics is by formal methods. I'll jump this citation. There are indeed many different arguments against the possibility of finding all the consequences of a program by means of purely deductive reasoning. The most straightforward argument is the argument of complexity, right? So in this paper, they say, back in the real world, the specifications for any reasonable compiler or operating system fill volumes, and no one believes that they are complete. The input assertions for these algorithms are not even formulable, let alone formalizable. So this is basically saying it's too hard, right? So if you look at this sort of argument in further inspection, although these arguments, they put an almost unsurmountable difficulty for this view, they don't really refute it, right? But a more crucial point is what was presented by a guy named Fetzer. This is a little bit long, but let's go over it. Algorithms, and you understand algorithms this way. So it's a specific definition. An algorithm is a logical structure of the type function suitable for the derivation of outputs when given inputs. So algorithms are subject to absolute verification by means of the deductive procedures. This possibility occurs because the properties of abstract machines can be established by definition. In this sense, the abstract machine under consideration simply is the abstract entities and relations thereby specified. In the other hand, programs, that is, a causal model of an algorithm obtained by implementing that function in a form that is suitable for execution by a machine, are merely subject to relative verification at best by means of deductive procedures. Their differences from algorithms are precisely because the properties of the abstract machine they represent stand for physical machines whose properties can only be established inductively. The very idea of program verification trades upon an equivocation. I'll try to translate this quickly. So in sum, this proof, any proof related to ideal entities does not apply unreservedly to natural ones. As put elsewhere, there is no way to deduce logically that bridges stand, that airplanes fly, or that power stations deliver electricity. So when a physicist or an engineer calculates the movement of a cannonball, he doesn't expect to have proven it, right? This refutation doesn't exclude the possibility of studying programs in an abstract way, but precisely because it is only considers them in abstract, it is not a science strictly speaking about programs. The mathematical ingredients involved in the movement of a cannonball don't talk about the movement, let alone about cannonballs. They talk about the parabola, right? That's the mathematical object. So, third, programming as engineering. So it seems that the failure of these two views to yield like a final method for programming, coupled, of course, with the growing need to solve immediate problems, has led to a more pragmatic view about what is programming. So, as Brooks puts here, the distinction between science and engineering lies not so much in the activities of the practitioners as in their purposes. A high-energy physicist may easily spend most of his time building his apparatus. A spacecraft engineer may easily spend most of his time studying the behavior of materials in a vacuum. Nevertheless, the scientists build in order to study. The engineer studies in order to build. So the way he pictures programming as an engineering activity also sort of give an explanation on why some people may think it's mathematics or science. This is because seeing it as engineering doesn't rule out the possibility of using these other methods, right? And in his account for an activity to be considered a form of engineering, we don't look at the methods this activity employs. We look at the purpose. So the purpose is to build something, therefore is not science or mathematics. These distinctions conform with this classical view of engineering of simply applied science. We have distinguished, for instance, chemistry and chemical engineering, biology, genetic engineering in the same vein. Even if these are sort of different from other forms of engineering in the sense that we build things that are natural entities, actually. We make animals, you know. But the problem is that this doesn't really solve the ontological problem. In the same way that, you know, saying that something is science doesn't make it so, just labeling engineering doesn't explain away the object that is in question. One alternative is actually to assume some more naturalistic view of what is a program, because the two previous presentations are sort of depend on abstract entities and so on. So one way of looking at it is this. A program is information only when it's executed. Before it's really executed as a program in the machine, it is handled, carried to the machine in the form of a stack of punch cards, or it is transcribed, it is just a bunch of data. So this is a very naturalistic way of looking at programs. No, just a bunch of data. The problem of this characterization is that it can account for the designer's intentions. To illustrate this point, imagine that there's this book, okay, that we know for a fact that someone wrote this book like a long time ago in a language that no one speaks nowadays. The thing is that we would still call this a book, regardless of the current possibility of it being translated, understood, interpreted. If we find a way to interpret this book in the future, we would say, now we can read this book, right? Instead of saying, now this book that was just a bunch of data for a long time is readable. And this captures our common usage of the word book. So we use this word conversely to denote a specific book or an abstract notion of book. When I go to a friend's house and I look at his books and I say, I also have this book, you know, I'm using in this abstract sense. I don't have exactly the same copy. And the thing is that software looks the same. We all have the same program. You know, we can copy this program, you know. And it's interesting because this nature is actually what creates countless issues for software as intellectual property. There are lots of debates in legal departments about, in the law about that. So the analogy of a program and a book is a highly valuable one, it seems, and it extends to many features of both, except when it comes to be able to causally influence the behavior of machines, which is something a book cannot. This can be seen as a difference in intent. While a book is written for readers and must be understandable by a human, or at least excite human understanding, like in Jabberwocky's case, you know, the poem that is like nonsense, it's still think it's literature, right? In the other hand, a program is written for a certain machine or a certain compiler that translates it into a certain machine to understand it. But even this distinction is not as sharp as it seems, because in the current engineering world, writing programs is a highly social enterprise. And the programs need to function not only as a machine instructor, but also as a means of communication between humans. Many modern languages try to be as close to natural language as possible, making the code readable. And many developers emphasize aesthetics in their practices. But since not all data is software, we need some criteria to distinguish them. The best criteria seems to be exactly the author's intent, since it preserves the identity of software regardless of the fact that it's being currently executed. There's a key difference in saying that when resting software is just data and that it can be seen as just data. When a program is compiled, for instance, it is taken as just data from another program. And finally, there's this common feeling between software engineers that this ontological question is not really relevant. So I would say that using Feyerabend's famous quote, this is the anything goes approach, right? So one quote from James Noble that was here yesterday. Our view is that computer science has come of age. Computer science is sufficient for itself, albeit as an unrestricted science from where investigations must be prepared to follow their problems into any other science whatsoever. Indeed, some key results on the discipline of software engineering, such as design patterns, seem to be judged simply by the criteria of projects applying them being successful. There doesn't seem to be any bigger reason to apply them. So the anything goes approach can include a posteriori justification, but it emphasizes the nature of programming as a practical activity. And prima facie, it is reasonable to take decisions based on purely practical grounds. The pragmatism of software engineering and its emphasis on human needs can't be captured better than in Brooks saying that swordsmith is successful whose clients die of old age. So the anything goes approach also advocates a descriptive worldview, that is, one that avoids metaphors and grand schemes. It sees the ontological question not so much as a question of nature of a program, but more as a futile attempt to find the most perfect analogy for what a program is. It also downplayed the roles of analogy in other fields, like in the design of the languages themselves. Like we have seen, analogies of object-oriented programming as Plato, Platonic forms, or even prototype-based as Wittgenstein, family resemblance, or recently I have seen some certain forms of functional programming as Whitehead's process philosophy, this sort of thing. So in the same paper, they have this criticism of this sort of analogy, which is it doesn't seem to make much sense to say that a bovine object in a program is an abstraction of a real cow in a farm. It doesn't make sense to say that the object in the program is implemented by a cow in reality, or that the objects in the program are special kinds of cows which do not eat, excrete, or expire. Alternatively, following Plato, we could have an abstraction of a cow as the ideal, immutable, eternal form of a cow, perhaps corresponding to the cow class. But again, this kind of abstraction is not a good description of the relationship between the cow object and the real cow. In the following part of this, they try to give an account of this relation, which is interesting, but the thing is that all these analogies, simply put, they are what people call lie to children, a lie to children, right? That is something that allows students to climb the first steps in a subject and only throw away the ladder later. But it is very common that we, in our deeply ingrained desire for simplicity, we commit this fallacy of analogy, confusing the analogy for the real thing, right? So within modern computer science, there is an intellectual posture that accepts metaphors from other disciplines uncritically, without providing arguments as to why that metaphor should be applicable. In general, this is the result of the modern grand narrative. Computer science must conform to some theory, where the theory is carried by metaphor. And also I have to say that Dijkstra has criticized harshly this role of analogy, especially on teaching computer science, because when we go to university, people try to find something familiar to explain these new concepts. So what he says is that it is the most common way of trying to cope with novelty. By means of metaphors and analogies, we try to link the novel to the familiar. Under sufficiently slow and gradual change, it works reasonably well. In the case of a sharp discontinuity, which he thinks computer science is, however, the method breaks down. Though we may glorify it with the name of common sense, our past experience is no longer relevant. The analogies become too shallow, more misleading than illuminating. The educational dogma seems to be that everything is fine as long as the student doesn't notice that he's learning something really new. More often than not, the student's impression is indeed correct. I consider the failure to prepare the next generation for radical novelties as a serious shortcoming. But again, the dangers of analogy only materialize when the latter is not thrown away. And given the educational benefits of analogical thinking, and maybe even the possibility that we can really get rid of it, we should maybe instead focus on being clearer, on clarifying these relevant features when any analogy is introduced. If you want one very interesting example of this sort of explanation, there is a paper by a guy called Antero Taivalsari. I don't know Finnish, so I don't know. And the paper is called Classes versus Prototypes. And the way he explains that object-oriented programming seems to embody this Platonical scheme for a very simple reason, is that a lot of our practical work when we're programming is related to the problem of ontology. That is, we need to define what are the elementary entities in our applications. We need to define their names, their functions, and their relations. So once we recognize that this is the relevant feature of this analogy, we can throw this analogy away. And what he does in this paper is that he even used this to advance a little bit the field, because he goes to more contemporary cognitive psychology, and he concludes that prototype-based object-oriented programming is more in line with current understanding, which is strange, right? Why we would draw analogies of like very old-fashioned theories that have nothing to do with reality. So now some final remarks. Whatever programming is, it is certainly a radical novelty in this sense that Dijkstra puts it. So this view makes it imperative for programmers to understand their trade in a deeply reflexive way. In the worst case scenario, this kind of knowledge may help us have better answers than the following to the question that there's this book, Coders at Work. So this guy asks for many programmers the question, do you think of yourself as a scientist or an engineer or a craftsman or something else entirely? So I'm putting this response to this question, not to mock the author, of course, but because I think this sad feeling is widespread in our industry and represents many of other programmers' feelings. So his answer to this question is, I see myself definitely not as a scientist or engineer because those are very formal connotations. I don't do a lot of math. I don't draw blueprints. I don't prove things. I write a lot of screensavers. Thank you. The text is on GitHub, so you can send pull requests, fork, make your own version. I don't know.
Hi. So one thing I'm curious about is what your thoughts are on design as being kind of an activity that's comparable to science and engineering. Because I know that like after some of the stuff Herbert Simon did, I think there was this whole movement of like design methods where people said like, hey, design is actually kind of a discipline, and it's a real thing that people do across all kinds of careers. And I see, after learning about this, I see this a lot in, I feel like as a programmer, that's largely what we're doing, not architecting or crafting or whatever.
Yeah, I think this just feels like a new breakthrough or something, because I think I don't know if you agree with me, but we use the word design in two different ways. Right? There's this idea that design is sort of related to, what web designers do, like that is purely an aesthetical thing. There's this sense of design. But if you look at the literature of epistemology of engineering, they use the term design to explain their method for like a long time. So, design starts with a problem. You apply certain reasoning to figure out how to solve this problem. You have to choose materials. You have to do all these steps. And nowadays you even have to think about the consequences of your products, like environmental issues and stuff like that. And yeah, I think that in this sense, when people say that the design is method of software engineering, they are equating with this engineering sense. That actually the other way we use design is also the same. We just have this, I guess, misconception.
So, don't you think it may be useful in the modern world to see programming not as a discipline, maybe, but as a kind of literacy that is kind of common foundations that is used by scientists, craftsmen, artists, industry professionals, not a discipline anymore, because the foundations are laid out already. It's kind of a literacy. Everyone needs to speak this common language. No?
I think this is like a different question, to be honest. I mean, of course, in the beginning I said that, like, programming changed all the other fields. And it means that it's not only programmers who program. Physicists program, everyone programs nowadays, Even when you do a spreadsheet, your user is sort of completing your program. You haven't built the whole program. So, of course, I mean, it is super important. What else can I say?
There was one slide that disturbed me, and that started with
that's good.
in the real world, everything breaks down, and you can't really trust anything. And
well, it's not about really trusting anything. They're just saying that you cannot, mathematically prove things because it's too hard. It's not like you cannot know anything.
But I think it's unfair, because even in mathematics you have assumptions, axioms, where you start and then you build from these axioms you build some kind of truth and proofs.
Yep.
And in the same way, I think you could at least think of a program as assuming that we have an operating system that always do this and this, then we can think of the program on top of that.
This is, I actually refer to this two things. One is that, as I said, you can see a program in an abstract way that's not problematic at all. I mean, think about a sphere in a mathematical context, right? Mathematics deals with the sphere. There's this equation that, you just know this equation about it. But then you have, in science, you care about movement of balls. And then in engineering, you try to make the best ball. If you're successful, you make like a World Cup ball, but we all did like a softball, which is shitty engineering, but it was fun. So mathematics deals with this object that is not in the world, that is the sphere, So what I said there is that when the problem is that when you look at programs abstractly, you're not talking about programs anymore. That's the main issue. It is useful in the same way that studying sphere is useful for understanding balls, but it's not the same thing.
Okay, thanks. So I saw the categories that you described, and I missed there one, which I was introduced to in OPSLA 2006 in a presentation by Martin Renard. So he classified the thinking into rationalistic thinking, empiristic thinking, which would be engineers and mathematicians, and clueless thinking.
Clueless?
Clueless.
Yeah, of course. This exists in, like, when you make like this sock ball, you're being clueless about the dynamics of balls and stuff. Fine.
Yes, if you just play the soccer, then you are clueless.
Being clueless is fun,
But he claimed that majority of programmers are clueless, and that's a reality that we need to be ready for.
Yeah.
And when I was, I sometimes talk about API design. I was saying that the role of the designer is to make sure that the framework created can be used in clueless mode, because that will really help do good engineering for majority of the people out there.
Yeah, so I think this is sort of embodied in this postmodern, whatever name you give view, because I don't know if you read The Big Ball of Mud paper. It's a great paper. So basically, I guess the idea of that paper is like, okay, in reality, people are doing this, not what you're studying. So why don't we sort of study this thing, understand it, and try to improve from there? But I guess that if I omitted this part because I have only 35 minutes. But I feel that if you go this way, you sort of your methodology sort of becomes a mix of all these things plus some social sciences, because what you're doing is sort of anthropology, like. You have to study programmers, how they behave and so on, which I think it's valid. I mean, This is why the defining programming is so hard, because this is also part of it, you know.
Okay, last question.
Okay, not so much a question as observation. You ended up with a slide about screensavers, and this accords with my own view that perhaps there's a fourth category, which is programming as artistic medium.
Yep.
And that's why it's so difficult to detangle the form and the the formal aspects from the physical aspects. But I had an illustration of your what is data, what is program. Way back in the day, there was this diff program that we had, which had a -e option, which would spit out an ed script, which was obviously program. And there was also a -c option, which would spit out a context diff. And everyone said, that's data for humans. And probably because the -e option existed, that actually blocked people from thinking, I could think of the context diff as a kind of program, which is instructions for how to update someone else's copy of it. And that was realizing that was a form of program was kind of the origin of the patch program, and realizing, oh no, the computer could actually take the context diff and interpret it and apply it. And so there you have a piece of data that was not thought of as program that actually turned out to be.
Yeah, so just a comment on your comment is that I actually, for the lack of time, I haven't evolved much on this discussion, but one of the papers that deal with this sort of data nature of programs, they sort of agree with what I said, like that the intentions of the programmer is what keeps data being a program through time, even if there's no existing way of executing it today. But they sort of give a very good counter argument, which is that if you see it this way, any data can be interpreted as software. It's just a matter of you building the parser for it. Even you can find a crazy way to make noise execute, You just need to create the parser for that. So it's like a counter argument that they try to deal in a different way, but I think it's a really interesting observation.
Thank you.